Hello, welcome, and an excellent evening. Here's part 2 of our AdLib programming tutorial, so to speak, using MS-DOS and Turbo C 2.0, as usual in the Let's Code MS-DOS series. In the last episode, we coded a simple AdLib-based drum machine using the OPL2 synthesizer by Yamaha, which is on that card, but is also basically on all the Sound Blaster cards and their clones. And it's a bit tedious at times to program this chip, but there's some good documentation out there, and I also found this very nice page, Cosmodoc. I will link to it in the video description. It has an excellent description of all the functions and ideas behind the OPL2. Especially also stuff like very good pictures for the waveforms. Basically everything on the OPL2 is based on a sine which is actually stored in a ROM-like fashion, at least the quarter wave, which is then duplicated by mirroring for the positive and negative part and the other half of the phase, etc. So yeah. There's also a very good explanation of the envelope generator with the attack, decay, sustain, and release. Also, when the key on and the key off comes into play, actually you can toggle that on the card, on the AdLib card. That took me a while to figure out the bit that is actually doing that. If the bit is off, then after the decay phase, the release phase will go immediately off instead of the sustain, which is similar to not pressing the sustain pedal on a piano, so to speak. And yeah, other nice examples with Fourier transformations or spectrograms of the different effects that you can have when using the modulator to modulate the carrier, and also an explanation what the vibrato and the tremolo functions, which is called amplitude modulation, on the OPL2, well, how they work basically. And yeah, I can definitely recommend that. And this time we will actually do some melodic programming. We are in the rhythm mode of the OPL2, which means we have 6 melodic voices and 5 drum voices. And I already put in a couple of stubs, mainly a function called AdLib set instrument, where we will introduce a structure called AdLib instrument, which takes the most important options for one instrument of one voice, one of the 6 melodic voices and their oscillators, and also a function called play note, which will play a specific note on the specific voice. And then we will introduce more keyboard presses here to have kind of a piano keyboard on our regular keyboard, basically by using the row of the letter keys A, W, S, T, and so on. To do that, and well, I also clean up a bit the register section and introduce all the registers that we will need today. So if you don't know what any of these mean, please check in with the first video in the series, and also with the documentation of the chip. Basically here we have most of the registers explained, including the per channel registers, which are the voices, the 6 that we currently have, and the per operator registers, which is basically one register per oscillator. So let's get started. First up, we need to define a couple of things. And the first would be the oscillators that are used for the different voices in the different modes. And we don't need to concern ourselves with the drums, but for the 6 melodic channels, we need to define that voice 1 uses, or voice 0 uses oscillators 1 and 4, 2 and 5, 3 and 6, 7, 10, 8 and 11. So let's code this. There's going to be a static int AdLib voice oscillator. The size will be 6 voices by 2 operators. And yeah, we're gonna call it up like so. First one has 0x00 and 0x03. This is oscillator 1 and 4, because we're 0 based obviously instead of this one here, which is a bit weird. They do a 0 based index on the channel, but the operators are 1 indexed. Doesn't make sense because the offset into the registers is actually 0, so it would have made more sense if they use 0 for both. But yeah, we can work around that. And next up is 0x01 and 0x04. Then we get 0x02 and 0x05. Furthermore, 0x08 and 0x0b. This is just copying the values out of this table here. Nothing more. And the last but one is 0x09 and 0x0c. Come on. And the last one is 0x0a and 0x0d. This way we can do a quick lookup which operator to use when we set an instrument. Furthermore, we need the frequency numbers. So this will be an unsigned int because we need how many? 10 I think bits. So we'll use that. And we call this AdLib notes. And this will be 1 octave. And I did write a program to figure out these frequency numbers because there is a long table at the end here with all the frequencies of all the notes for octaves 1 through 8, with 440 being A5, basically. And I figured out that since the block numbers are equal to the octaves, we don't actually need to code all the frequency numbers, but 1 octave is enough. The only thing where this differs is, I think, let me look it up, the F8. So this note here has a slightly different frequency number, which would be off by 5 Hertz, I think. But I'm not gonna bother with that. So you can just code the frequency number for 1 octave and then just set the block number in the register and you're mostly good to go. You can do a table with all the correct numbers, but I leave that to you to do that. So if you write this program or put in the values into the formula manually, whatever you like best, the formula being this one here that we talked about, I think, in the last video, you will get as frequency numbers 172, 182, 193, 205, 217, and I think I'm gonna put a space in there as well, and 230, 243, 258, 273, 290, 307, and 325. That's that. Those are all the notes that are in 1 octave, basically. And now we need to define a structure to store our oscillator options. So we call it AdLib oscillator. And this will have parameters for the attack rate, decay rate, the sustain level, and the release rate. Then we will have one bit each for the AM and the vibrato, if they are on or off, or maybe there are 2 bits, I forgot. Might be also level for that, I'm not sure. But for all these options, a char is good enough. There's also the sustain bit, This is actually really a bit which determines if the sustain level is actually used, as long as the key is pressed on. If the sustain bit is off, the sustain phase will be skipped and the release phase will immediately begin. It's similar to pushing the sustain pedal on a piano, basically, before hitting the note. So on a piano, it's if you hit the sustain pedal and hit the key, as long as you press down the key, the tone will sustain. And yeah, it will eventually fade off on its own, but it will continue sounding, because if you release a key on a piano, there will be a little damper that will stop the note from being continued, basically by stopping the string from vibrating. Something like that. Then we have the key sustain level, which is basically, I think, an additional attenuation factor for the sustain. And the total level, which is an attenuation on all of the ADSR, making everything quieter, basically. And we can choose the waveform. This is the wave select. In the code that I'm checking in, there will be comments which is which, but I'm gonna skip that for now. You will see that in a moment. We use the oscillator to define an instrument. So we have an AdLib instrument. And one AdLib instrument will have two oscillators, namely one called carrier and the other the modulator. And we'll also have a bit for the connection between those, either having the modulator modulating the carrier, or if the bit is set, you will have a connection where both are just added together. This is additive synthesis, and it sounds much more clean and maybe even boring. And there's also the feedback bit, which means that the output of the combination of both modulators will be fed back in, attenuated, into the original signal, giving rise to some distortion, basically. Yeah, this you can toggle as well. Then we need to be able to do the set instrument call. And that's actually relatively forward. It's just a bunch of bit manipulation. So what you need here is the, let's zoom out a bit. You need the registers here, and always have a look where each of the instrument and oscillator definitions goes. So input is an instrument structure and a voice number, basically. So first of all, we are setting the ADSR for both oscillators. We're doing this by calling the AdLib register routine on the ARDR register. Plus, let's check this, attack rate and decay rate are 16 registers, so that's one for each oscillator. So we'll use the AdLib voice oscillator array that we just created and take that for the first oscillator. And we are looking up the modulator, because the first oscillator is the modulator, the attack rate, and we will end this with 0xf to definitely limit it to the values 0 to 15. If the user puts in a larger value, it will be clipped and not write garbage into the register. And the attack register is actually the higher 4 bits, so we need to shift this by 4. And we need to combine this by using the OR operator with the decay rate, which is instrument modulator decay rate, and this will also be limited to the values 0 through 15. And those are already the lower 4 bits, so we can close that. We can copy this whole thing to voice 1 to get the same basically. And we can copy it 2 more times if I manage to do that, to actually also do the sustain level and release rate for both. So let's do this here as well. And for that we obviously let's take a look. What are the high bits? The high bits are the sustain level. So it's very similar to what we did before. And the low bits will be the release rate. Very straightforward. That should do it. That's the ADSR curves for both oscillators. You can use different ADSR rates if you want to, but for simplicity's sake, we're using 1 for both oscillators. Then we're gonna set the sustain, amplitude modulation, and vibrato, which works in a similar fashion. There's one register to set all of that. It's the AdLib register AM vibrato, EG, that's the sustain, KSR, and multi. Those are quite a lot of bits. Here you see tremolo, vibrato, sustain, key sustain rate, and frequency multiplication factor. There's a couple of things that we don't set here that you can play around with, like the multi, but not going to do this here. Leaving this up to you to do as a homework, basically. Same goes for this. This is per oscillator, so we do AdLib voice oscillator for this voice. And for oscillator 0 first, foremost. And then we begin our journey. First we need to do the tremolo, which is the amplitude modulation. So we take instrument for the modulator and the AM value of the same, shift it 7 to the left because it is bit number 7, as you can see. And I'm gonna kill this bracket and close it at the end. And then we OR this with the instrument. Oh, there's an error. We need to do the arrow because it's a pointer. Instrument mod vibrato is the next. Shifting this 6 to the left because it's a 6-bit. And combine this with the sustain bit, which is the 5th bit. And that's all we are setting here. We ignore the other values, we leave them at 0. Then we can copy all of this, and I'm gonna do a little test compile in a second, for the carrier, which means we have to replace all the modulator occurrences here with carrier, and then we have all the values for all the different oscillators. There's 2 errors. I have done something wrong. Extra parameter and call to AdLib, register and function, blah blah blah. Oh yes, because I put a comma in here, which is bad. Okay, we have some warnings because we're not done coding yet. So far so good. Those are pretty long, those lines, so it takes a bit. Next up, we have the key sustain level and total level that you can adjust. I'm just gonna copy both of this because this is also, I think, for both oscillators, key scale and total level, yes. Although here we have multiple bits, 2 bits here and 6 bits there, but we can use that. And let's only copy one. The register is called obviously slightly different. I think it's KSL and TL. We need to use again the lookup here. And we are taking modulator KSL, shifted to the left by 6 because we're using bit 6 and 7. And then we need to use modulator. Let's kill one of these instances. Instrument modulator TL, shifted by nothing. However, I think I'm gonna, let me check. Yeah, I'm gonna AND this to 0x3f, which is, I think, 64. Does that make sense? Does that make sense? I think I should have used something different, right? Because let us pick up a, do I have binary here? No, I don't. So I'm gonna use my Swiss Micro. 3F is 63, which is actually correct. 3F is 63, that is all the 5 bits set to 1. So that's why I'm doing the AND here, to just mask it off. If you put in anything bigger than 63, it will be clamped. That's always a good idea. Okay, let's copy this and do that also for the second oscillator, for the carrier. And that's that. Usually, mostly you will not change this, but maybe you want to have the modulation a bit weaker, so you would put something different from 0 into the values for KSL and TL for the modulator if you don't want to have heavy modulation, basically. Then let's do the waveform select. So AdLib register, AdLib, what is it called? Register WS. That's actually a pretty empty register, I think. I think there's only 2 bits that are used, the rest is unused. So again, AdLib voice oscillator for this voice. And operator 0. We're going to take instrument dot, no, not dot, arrow mod wave select. And we're using 0x03 to mask exactly only those 2 values. And that's that, and I think we don't even need the brackets here. And we're doing the same for voice number 1. And doing the carrier here as well. And now the last bit is connection and feedback. Connection and feedback are in which one? In which one? In which one? Which one? Let's see. Question. Connection and feedback. Feedback. Oh yeah, here we have it. C0 through C8, that is a per voice and not a per oscillator. And you have 3 bits, D1 through D3, for the feedback. So 8 different levels. And the additive bit, it's called here, not connection. Well, some call it connection, here it's called additive. So it's the AdLib register FBC, that's what we called it above. And we're using the voice as an offset, because it's per voice. And we're using instrument feedback shifted by 1, and that should probably and this as well, but since the rest of the bits are unused, I don't care that much right now. And the instrument connection bit, and we will clamp that, otherwise it might interfere with the feedback. So that's that. That's pretty good. Should still compile. Yes, with a couple of warnings still, because we have some empty functions. Play note. That's relatively easy as well. But I will do it a little bit different. Let's begin as follows. The note on value basically will go something like this. We will need to do AdLib register on AdLib register FNL, which is the frequency number, the lower bits, frequency number lower, that's FNL, for this voice, because you can only set it for the voice. And this will be the lower 8 bits of the note. And we will need to do the key on and the higher bits and the block number. So this is the register. This is all in one go. Register key on, block, and FNH, the 2 high bits. This is also per voice. So the key on is 0x20. We already know that from the drums. And we will combine this with the upper 2 bits from the note. That is, this is just the note shifted 8 bits to the right. And that's that. All right. This will at least change the frequency, but before you do the key on, you need to do a key off first. Otherwise you do some kind of portamento, which is possible, but not wanted here. So what we'll do is we'll do a key on and frequency. We'll do some kind of key off event first, because the good programming would be to use our low-level keyboard interface and to see if we have a key on event or a key off event. I leave that as a homework to you. Here I can only determine if a key was pressed, and then the note will be on until I press another key, which is not very realistic, but that's how we do it right now. So you can change that to make it nicer. And we will have to do something like this. Right into the key on, block, and FNH, plus the voice, basically. And normally you would just toggle off the bit, basically, that was in there. The problem is it will also change the pitch if you don't know the pitch that it's currently at. So what we're gonna do here is we are gonna introduce a little static array which will keep its values between function calls, and we will store the frequency here, basically, okay? And since we only have one block, we're using always the same block, you can't change it, we don't need to store it here. That's why we store only the frequency here. Even though we can, I think we can even do that here. Yeah, I think we even store the block here, but it wouldn't even be necessary. But we're initializing this with 0 per channel because nobody's currently playing anything on any of the channels. And what we're doing is we are taking the voices entry for this voice, shifting it to the right, just as we do down here, and then turning off the bit for the key on. This we can do by doing an AND with 0x1f. This is 20 hex minus 1, which leaves all the other bits on, but forces the key on bit off, basically. And the block number and the F num high will stay the same, so that the pitch doesn't change, which would sound very weird. But once we have the new key on value, we will have to store our current note that we have played. So we just store that here, and that's that. And this will do a very nice turning off of the note and then turning on the voice with the new note, basically. And this is something you can also reuse if you use our low-level keyboard interface to do different AdLib play note and turn off note functions, basically. Then you will have one shared array for the voices. The play note function will set the frequency, and the stop note function will use that information to not change the pitch and turn off the key, basically, because once you do the key off, the release phase begins and the note will start to gradually turn itself off, which is much nicer. All right, does this still compile? Yes, it does, and we have less warnings. So on to the next thing. This is already all the functions that we need. We can now start to define more things here. First of all, besides the drums, we also need an array to store the notes that are being played. Again, 512 notes at the most. And we will also have to initialize that to 0. So notes, comma, 0, comma, takes times size of an unsigned integer, because these are not bytes. This will set all the notes to 0. Then we need to define an instrument. And I already put that up here, AdLib instrument inst. So first we define everything for the carrier. First the amplitude modulation or tremolo. I'll set this to 1. And I'm gonna type down here a couple of parameters, and I suggest that you play around with those. I'm not gonna explain them fully here. Basically, mostly the higher the value, the shorter the time, or the greater the effect, like attenuation, things like that. So a 0x6 will be a medium fast attack rate. 0x1 would be a very slow, 0xf would be a very fast or instantaneous attack, and 0x6 will be relatively slow in the middle somewhere. And you can play around with these numbers to make everything sound more interesting and get very different results. So I'm gonna type this down without a comment and be back in a minute when we've done that. Okay, here we are. This is it, and I've turned on the modulator sustain bit to get a sustain onto this instrument. As I said, you can play around with these settings and get very different results, sometimes also a bit confusing, but it's always pretty logical if you think what these all affect, basically. We also should set up the connection, basically. I'll put that to 0 to get FM synthesis and not the additive synthesis. And the feedback I'm currently turning to 0. You can use a higher value to get more feedback and probably a dirtier sound. And then we'll set the same instrument for all the voices. Basically, the reason being that we want to have like polyphony, that you can have 6 notes of the same thing playing at once, similar to a piano or something. And we are limited to 6, obviously, because there are no more melodic channels in here. So calling the set instrument function here. And then we will have a ton of new keys, basically, after the drums. I'm going to insert here one example and then copy in the rest, basically. I will use the keys A, W, S, E, and D for the first 5 notes in the octave, then F, T, G, Y, H, U, and J to have the remaining 7 notes, so that you get the same arrangement like on a piano keyboard, basically. So we're inserting into the notes array, and we will have to set the block that I've set above. You can change that to get a different octave, obviously, shifting that left 10 bits because those are the higher ones. The bits 11 and 12 and 13 basically. And then using our AdLib notes array for note 0 and masking that to be on the safe side to 3FF, which is 1023. And that's that, and then we'll break. And now we can copy this, and we only have to increment our first put here our W, which is the next note, half note higher, and then do it like that. And I'll be back once I copied everything. Okay, that was quite a bit of copy-paste, but it's all looking the same. And I don't think there's an much easier way to do this. Maybe with some other array for mapping those characters to the numbers 0 to 11. That could have been done, but I was too lazy. So yeah, you can perhaps update that if you want. Yes, the other thing that I had been inserting here is to show if the drums are playing, things like that. I think we can do something similar for the notes. So if there is a note at this position, we can also print something out so that you can see, there's something playing. And we actually need to call AdLib play note, obviously, because that was still missing from the notes at this particular tick in time. And I'm using this trick here, to switch between all the 6 channels depending on the tick number, basically. I should probably just use a rolling counter to get an actual polyphony that works. Yeah, let's do that. I think that's actually better. Let's insert here something like current voice equals 0. We start with 0. We use current voice, and then we will do something like this. Current voice equals current voice plus 1 modulo 6. This way we will always have something between 0 and 5, which makes sense. Okay, I didn't think of this before. That's a good thing that we do that now. And we also will print a hash mark to indicate that a note was played, so you can see it flashing on the screen when a note is played. Otherwise, we will just print an empty space so that the screen doesn't get garbled. And I think that's it. Let's build this. It works, and we can also try it out. I need to turn up the sound here a bit. As you can hear, it works. Also, compared to the last time, I added an AdLib reset at the end because the notes were still hanging on after quitting the program, so this is much better. We can also try to play chords, but you have to press the keys one after the other, more or less, because we can only detect single key presses. With the low-level keyboard interface, you could also do multiple key presses. Yeah, naturally I can't play, so the best I can do is probably this. Good, I'm not gonna bore you with this anymore. I think video has become long enough, but you know all the basics now. You know how to set up an oscillator or both oscillators. You can put more of the parameters in if you want to. You can play around with the waveforms because they will change a lot how everything sounds. For example, let's very quickly change the carrier to a simple sine wave. Then it sounds more like an organ or something. Or let's change it to, I think this is the pulse, the square wave. Yeah, you can hear that. Or let's turn off the sustain, for example. This will sound very different. Oh no, this actually continues pretty long. Yeah, there's probably some. Okay, the sustain level here is probably very fast. Let's very slow. Let's turn this off and this off. Yeah, now it sounds pretty different. Yeah, you can play around with all of these. You can perhaps even create a keyboard interface or an instrument editor to do that. But you know how to play notes, you know how to calculate the frequencies, how to set up the instrument, and then how to play a note, turning it on, turning it off. And that's basically everything that you need for doing music in AdLib. Of course, you will need to be able to compose pieces. There are editors out there that can target the AdLib card. There's the AdLib Tracker 1 and 2. There's playback routines. There's the RAD player. Similar things. Or you can code your own, obviously. And you need someone with a bit of a musical talent. That will be not me, but I hope you learned something. I hope you will share, like, and subscribe, the usual stuff. Leave a comment. And yeah, thank you very much for watching, and see you in the next episode.